So here it is, fundamental theorem of calculus. It is a big deal. Okay, so I'm going to talk about part one, and there's a part two here. The part one proof is going to take quite some time. Okay, so first it's talking about a function f that's continuous on AB. And here's the function f that's inside the integral. And that you know to find the area under curve, the function has to be continuous. And that's what this integral means, right? So this is saying it's got this weird function g of x. So here I've got a, here I've got x. Here is my f of t function, right? And g of x is the area under the curve. That's very different. So that as x changes, this area is going to change. Okay, so there's my function g of x. So what, and so it's, so they're saying that this function g of x is continuous and differentiable. Okay, so what I need to prove is that the derivative of g is f. The derivative of g is f. Okay, so let me come up to this page up here, and because it's blank up here, so I'm going to show the derivative of g is f. Okay, so let's go back to the definition of the derivative. So the definition of the derivative, and I'm going to do it with g, is the limit as h goes to 0, g of x plus h minus g of x all over h. Okay, so I've got the graph or the picture right here of what g of x is, correct? So I'm going to say limit as h goes to 0. So g of x plus h means put in x plus h everywhere there's an x. Well, the x is up here, right? So this is going to be a to x plus h of f of t dt minus g of x, which is a to x of f of t dt, and that's all over h. This is kind of messy, so let me fix that. So this up here is x plus h. So let's think about this. I'm going to draw another picture. So here's a over here, here's x, and here's x plus h. I'm just drawing it large so that we can see the difference. Okay, so this is saying take the area between a and x plus h all the way over here. This is saying subtract off the area between a and x. Oh, we've done things like this before. So what's left? The area between x and x plus h, right? So I have limit as h goes to 0. And I'm going to pull this h that's in the denominator out front like this. And then these two integrals combine to give me x to x plus h of f of t dt. Okay, so I'm going to draw yet another picture of this x. I guess I didn't really need an x-axis or a y-axis here. So here's x, and here's x plus h. Okay, so I'm going to just draw this. Okay, so I'm going to go over some another theorem that I've touched on in lectures before. So because this is a continuous function, there is some lowest value. I'm going to put an axis here just so I can see it. There is some lowest y value that this function encounters between x and x plus h. So I'm going to call that little m. And between x and x plus h, there's some highest y value, and I'm going to call that capital M. All right, so I know that the area under the curve between x and x plus h, which is this, right, is going to be smaller than or equal to the big rectangle, capital M, times the width from here to here. And what is that width from there to there? That would be x plus h minus x, so that would be h. So this area under the curve is smaller than this huge rectangle. Then this area under the curve is going to be bigger than this rectangle that has height little m and width h. I think this looks very similar to when we did the squeeze theorem, isn't it? When we had something in the middle and we wanted to find the limit of, look at that. We do have something in the middle we want to find the limit of. So remember, we want to build this function in the middle. So I see that I've got h on both sides, so let's put it. Let's divide everywhere by h. F of t dt, and that's less than or equal to capital M. Okay, so let's think about this. So little m and capital M are values on the function, aren't they? Because it's a continuous function. So that must mean there's some x, I'm just going to call it u, that gives me little m. So I'm just going to put f of u there. And same thing over here. I'm going to make, there's going to be some x value there that gives me that capital M, and I'm going to call it v. All right, so how do we do this squeeze theorem? If I want to find out what this limit is, the one in the middle, what I do is I take the limit as h goes to 0, because that's what this problem says, limit as h goes to 0 of f of u, and I take the limit as h goes to 0 of f of v, right? These two outside functions. So let's see what happens. So if I'm going to let h go to 0, and h is the distance between these two functions, so it's like saying let this go here. So if I let this go here, where does u go to? U will go to x. So if u goes to x, I get f of x. And same thing, if I let this go to here, right, h going to 0, where does v go to? V goes to x. So I get f of x. So what does that mean about the one in the middle? It equals f of x. And what was it that I was trying to prove? Oh yeah, there it is. So the derivative of g is f of x. Okay, so that might not feel so satisfying, but it is a big deal. And this combination of a derivative and this really special kind of integral with an x in it is the Fundamental Theorem of Calculus Part 1.